So we are beginning with chapter 2, electric potential and capacitance. And this is lecture 1 for this particular chapter. So we need to understand from where the concept of electric potential came in, and in the much later segment we will be beginning with capacitance. So if we talk about the concept of potential energy, so it was first of all introduced in mechanics in connection with the conservative forces such as gravitational force and the elastic force exerted by a spring. Now by using the law of conservation of energy, we can avoid working directly with the forces when solving the problems in mechanics. So similarly, the concept of potential energy is also going to be of great use in the study of electricity, because electrostatic force is also conservative in nature, and electrostatic phenomena can be conveniently described in terms of electric potential energy. So with this idea, we will be beginning with the concept of electric potential. So over here, the first thing which is of a notable type is this fact that the electrostatic force is an example of conservative force. So we say that the electrostatic force is an example of conservative force. Now the next important statement which I am going to make is the potential is the characteristics of the field only and is independent of a charged test particle that might be placed in the field, whereas potential energy is characteristics of the charged field system due to an interaction between the field and a charged particle placed in the field. So we will come to this understanding of this statement later. So let us first of all begin with a basic problem. So let us consider that there is a electrostatic field, something like this, present in space, which I am referring it as E vector. Now if suppose a charged particle, a test charge, is taken from a point 1 to a point 2, so we need to calculate the amount of work done in order to move this charge in an electrostatic field by an external agent slowly. So the word slowly is introduced so as to make sure that there is no change in kinetic energy. And since we are saying that electrostatic force is an example of conservative force, we mean to say that the work done is going to depend upon the initial and final position and is independent of the path taken by the charge. So this is the first point which I can write over here, that since it is conservative in nature, the work done depends upon the initial and final position only. The initial and final position only. So since the charge particle is taken slowly, so I can write over here the following statement, that the work done by electrostatic force field plus the work done by external agent is equal to change in kinetic energy in accordance with the work energy theorem. Now since the charged particle is taken slowly without bringing about any change in kinetic energy, so we are equating it to 0, and then I can write that work done by electrostatic force field is equal to negative of work done by external force, which is moving the charge from point 1 to point 2 quasi-statically. Or the reverse is also true, that the work done by the external agent is equal to negative of work done by electrostatic force field. So using this we can say that work done by the external agent or the external force is equal to negative of electrostatic force into displacement, that is dr, from position 1 to position 2. And hence we can modify this equation in this way, that work done by the external force is equal to minus q integration of E dot dr, and this is from position 1 to position 2. So this statement is going to help us in formulating further equations about the electric potential. So let us move to the next page. So now we are coming to the definition of potential and potential energy. So first of all we will be discussing potential. So let us begin with potential. So now from the previous expression it was clear that the external work done is equal to minus q integral of E dot dr from position 1 to position 2. Now if I define potential, then potential is defined as the amount of work done by the external agent in slowly bringing a unit positive point charge from infinity to the observational point, or any point P for that matter. Now considering this statement, we say that the potential is regarded as work done per unit charge in bringing the test charge, which is obviously a point positive charge, from infinity to the observational point. So using this I can say that between the 2 points we can say that potential can be written in this way, that potential at a point is equal to minus of E dot dr. So we have divided that by per unit charge, so we have put q equal to 1, and it is from infinity to a point P. Or we can define potential difference between the 2 points considering that the work done per unit charge is equal to negative integral of E dot dr from position 1 to position 2, and we are calling this as dV, which is potential difference between the 2 points, that is 2 and 1. And hence we will obtain an equation like this, that is V2 minus V1 is equal to negative integral of E dot dr from position 1 to 2. So this is the equation which we have. Now since while defining potential I am again stating the definition. So it is defined as the amount of work done by the external agent in slowly bringing a unit positive point charge from infinity to the observational point. So we can move ahead, we can solve either this expression or this expression. So this equation is going to be of utmost importance for us in the further study of electrostatics, and hence I am using this expression. So if we begin with this expression, so I can write that V2 minus V1 is equal to negative integral of E dot dr from position 1 to position 2. Now we are writing it for a point charge. The value of electric field is equal to kq by r square, and hence we can say v2 minus v1 is equal to negative integral of kq by r square dot dr from position r1 to r2, and this equation will modify itself into minus of kq integration of 1 by r square is minus 1 by r, and hence we will obtain minus 1 by r2 plus 1 by r1. Now according to the standard reference configuration, so the reference which we use most often, so the reference which we use is potential is equal to 0 at infinity. So potential at infinity is considered as 0. So if we define potential with respect to infinity as 0, so I can say that if I say that the position 1 approaches infinity, that in this expression, if I say that R1 approaches infinity, then V1 will become 0 and V2 can be regarded as potential at a point with respect to a position R2 which is equal to R. So if we substitute the value over here, then this value is going to become 0 and the two negatives will multiply together to give us a positive value, and we will obtain the potential at a point V due to a point charge is equal to kq by r. So this becomes the value of potential for us due to a particular point charge. Now since we define that potential is a scalar quantity, so if there is a collection of charged particles, so we are dealing with the next aspect due to collection of charges, the potential at a point can simply be written as the sum of the potential of all the individual charges, where the potential due to positive charge will be written as positive and that due to the negative charge will be written as negative. For example, if we consider that there are three charges plus q1 minus q2 and plus q3 present in a system, so with respect to these charges we can define potential at a point P as potential due to q1, potential due to q2 plus potential due to q3, and it can be written as kq1 by r1 minus of kq2 by r2 plus kq3 by r3, where r1, r2 and r3 is the separation between the position of the charge and the point P respectively. So let us deal with the first problem. Two charges 5 into 10 to the power minus 8 coulomb and minus 3 into 10 to the power minus 8 coulomb are located 16 centimeter apart. At what point or points on the line joining the two charges is the electric potential 0? Take potential at infinity to be 0. So if we solve this problem, we are considering it in this way, that the charge q1 is situated somewhere here and the other charge which we are talking about is situated over here, that is Q2, and the separation between them is D. The value of charge Q1 is equal to 5 into 10 to the power minus 8 coulomb, and that of Q2 is minus 3 into 10 to the power minus 8 coulomb. The separation between them D is equal to 16 centimeter, which is equal to 16 by 100 meter. So let us consider that the potential is 0 at a point P, which is at a distance r from the first charge, and hence this separation is going to be d minus r. So if potential at P is equal to 0, and since charge is a scalar quantity, so I can write it in this way: k q1 upon r minus k q2 upon d minus r is equal to 0, and hence we will obtain the expression 5 into 10 to the power minus 8 upon r is equal to minus of 3 into 10 to the power minus 8 upon d minus r, that is 16 by 100 or 0.16 minus r equal to 0. Now on solving from here, we obtain the value of r equal to 0.1 meter, which is equal to 10 centimeter. So therefore the potential is 0 at a distance of 10 centimeter from the positive charge. Now if we look at another point where the potential can be 0, so we are considering a point towards the right of Q2. Now it is because this charge is pretty large, and near and beyond this, that is on the left hand side, the electric potential cannot be nullified by a smaller charge. So that is the reason we are taking another point on the right of Q2. So in the same, let us draw another diagram. So we are drawing the same system, that is charge Q1, which is equal to 5 into 10 to the power minus 8 coulomb, and another charge minus Q2, which is equal to minus 3 into 10 to the power minus 8 coulomb, and they are separated by d distance, which is equal to 16 centimeter. So I am considering distance s from the charge Q1, where the value is going to be 0. So that is at a point P, where we consider that the value is going to be 0 at a point P. So this distance from the charge Q2 will become s minus d. So if I write the expression or equation for this, again the potential is a scalar quantity. So if potential at P is equal to 0, then it is due to the positive charge, that is k 5 into 10 to the power minus 8 upon s, and the negative charge, that is k 3 into 10 to the power minus 8 upon s minus d is equal to 0. So if I put the value of d, so we obtain 5 into 10 to the power minus 8 upon s is equal to 3 into 10 to the power minus 8 upon s minus d, which was equal to 0.16. And hence from here we obtain the value of s as 0.4 meter, which is equal to 40 centimeter. So therefore the potential is 0 at a distance of 40 centimeter from the positive charge outside the system of charge. So we obtained 2 points where the value of potential due to the system of charge can be 0. So let us deal with the next problem, The next problem is stating a regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. So if we consider this problem, we draw the setup in this way that for a hexagon, all the sides are equal. So for a hexagon, all the 6 sides are equal, and if we join the 6 sides with the center, then we will end up getting 6 equilateral triangles inside it. So if we join all the sides together, we obtain 6 equilateral triangles inside it. So each point charge is having a value of 5 microcoulomb, which I am referring as Q, and the side length is equal to 10 centimeter, and hence each of this side being equilateral triangle will become equal to 10 centimeter. Now since potential is a scalar quantity, we say potential due to each of them will get added up, and hence I am writing that the value is going to be 6 times kq by r, where r is equal to 10 centimeter. So if we put the value, we obtain potential at the center as 6 times of k, that is 9 into 10 to the power 9, into q, 5 into 10 to the power minus 6, upon r, which is 10 centimeter. We are writing it as 10 by 100, and hence we end up getting 2.7 into 10 to the power 6 volt. So now we are going to come to the understanding of the equation which we have obtained, that is the equation of potential difference in uniform electric field. So we are dealing with the equation of potential difference in uniform electric field. So if we write the equation, so we write it as V2 minus V1 is equal to negative integral of E dot dr, and the value of this limit is from 1 to 2, that is from position 1 to 2. So this is the value of the potential difference equation which we obtained from the previous few examples. So if we consider the following things, the first one, if electric field is constant. So if electric field is constant, then we can simply write that potential difference is equal to minus E and the separation between R2 and R1. Or we can say that V2 minus V1 upon R2 minus R1 is going to give us the magnitude of electric field. In the next point, I am mentioning something like this, that if E is equal to 0, so if E is equal to 0, then the RHS will become equal to 0, that is V2 minus V1 is equal to 0, and hence we say that the region is equipotential. This is a very important point. So if electric field is 0, the value of potential not necessarily be 0. Not necessarily be 0. The region can be equipotential. that is V2 is equal to V1. Although there is a possibility that V2 is equal to V1 is equal to 0, but that is one of the many possibilities that are there. So but we say that if the electric field is 0, the region is equipotential. Let us move to the next point. So the next point, or the third point which we state over here, is the negative sign in this expression is signifying that the electric field is in the direction of decreasing potential. So we say that the electric field is directed in the direction of decreasing potential. In the direction of decreasing potential. The next point which we state over here is that if potential difference, that is V2 minus V1, is equal to 0, so then what is going to happen? So if V2 minus V1 is equal to 0, so we can say that this is equal to integral of E dot dr from position 1 to 2, that is also equated to 0, and hence there is again two possibility. So the first possibility is that if potential is 0, then electric field becomes 0 is one of the possibility, and the another one is if V2 minus V1 is equal to 0, that the surface is equipotential, then the electric field is perpendicular to equipotential surface. The electric field is perpendicular to equipotential surface or equipotential regions, that is E perpendicular to R dr. And since E and dr is in the dot product inside this integral, and two vectors when perpendicular to each other will give us a dot product 0, and hence we can say that the value V2 minus V1 is equal to 0 is justified on the left hand side. So these points are the few notable points which must be added with the points which I mentioned while teaching chapter 1 about the concept of electric field lines. So in the previous chapter we have learnt about the basics of electric field lines, that is, they originate at positive charge and terminate at negative charge. They do not intersect or crisscross each other, and the direction of electric field at a point is given by drawing the tangent at the electric field lines. So over here we have made necessary contribution to those points, that is, the electric field is in the direction of decreasing potential, it is perpendicular to the equipotential surface, and if the value of potential is 0, then the value of electric field not necessarily be 0. The region can be equipotential. So in order to understand the concept which we have learned, we are taking a small example. So let us consider a 2D space, and let us consider that this is x-axis where the distances are marked in regular interval, and we are drawing equipotential surfaces like this. So these are the equipotential surfaces which we are marking in the plane. So we are referring it to as 10 volt, this one is 20 volt, this one is 30 volt, this one is 40 volt, and this one is 50 volt. So if the distances marked are in centimeter, suppose 10 centimeter, 20 centimeter, 30 centimeter, 40 centimeter, 50 centimeter, and each of these equipotential lines are making an angle of 30 degree, then the question that is asked is, find the magnitude and direction of electric field. So if we use the concepts which we have learned, So the first thing which I can say is that the electric field lines are perpendicular to the equipotential surfaces. So if they are perpendicular to the equipotential surfaces, then they will be somewhat like this, that is making an angle of 90 degree with each of these surfaces. With each of these equipotential surfaces, it will make an angle of 90 degree. So I can draw more electric field lines. So these are the electric field lines we are talking about. Now the next thing we say about the electric field lines is that they are in the direction of decreasing potential, and hence the direction of electric field is in this direction, that is in the direction of decreasing potential, that is 50 to 40, then 30, 20 and then 10. So now if we say about the direction of electric field, so we can say that the electric field is making an angle of 120 degree with x axis. Electric field E vector is at 120 degree with x axis. Now comes the calculation of the magnitude of electric field. So if we can draw any of this triangle, so I am drawing it in black over here, which I will magnify later. So if we consider a triangle like this over here, so we can say that the separation between these 2 points is 10 centimeter. This angle is 30 degree and this one is 90 degree, and the electric field is in this direction. The value of potential difference between these two ends is equal to 10 volt. So the first thing that we need to do is we need to calculate the distance between these 2 points. That is, I am calling it as point A and B. So in order to calculate the separation between AB, so we are taking sine 30, which is equal to AB by 10. And hence we obtain from here that AB is equal to 5 centimeter. So the value of potential difference is equal to 10 volt. So if we use this expression that V2 minus V1 is equal to negative integral of E dot dr from position 1 to 2, and since electric field is constant in this region, so we can say that the value of potential difference is equal to 10 volt, which is equal to magnitude of E, and the separation, which is 5 centimeter. So we are writing it as 5 by 100 meter, and the value of the magnitude of electric field is 200 volt per meter, and is making an angle of 120 degree with the x axis direction.